My name is Tariq Yusuf. I'm a recent graduate from the University of Washington, and today we're going to be talking about surgical robots. So, a quick show of hands, how many of you have seen the 2013 film Ender's Game? A couple people. So, this is a scene from the film in which some kind of robotic surgery is being depicted as taking place. The robot in this film is actually a real surgical system being developed earlier at the University of Washington and now spun off into a new startup called Applied Dexterity. Now, we know so far that the use of robots in medical procedures have been shown to produce better outcomes as well as faster recovery for patients involved. But the current state of robotic surgery looks a little bit more like this. This is the Da Vinci system where you have one or more surgeons on one side, a few feet away from the robot that is being supervised by a nurse. So what Raven, this device, can potentially be, it can lower the cost and make these devices a lot smaller, so we can deploy them in unreliable, in areas where there are unreliable power or network infrastructure. So some of the places that come to mind are underdeveloped rural areas, sites of natural or human-caused disasters, as well as battlefield and military applications where time is critical. So let's look at what this diagram looks like. So in the bottom left corner here, we have our hospital. And this can even be just a simple office building with a computer controller. The surgeon performs the various operations. It goes through a communication channel over to the robot where the actual operations take place. The robot collects information about touch feedback, status of the surgery, and video feedback, and transmits that back to the hospital where the surgeon continues operation. One example of this, suppose someone in Alaska needs neurosurgery. Now, the University of Washington Medical Center, say, is the center of neurosurgery for Washington, Oregon, and Alaska. Instead of having to pay to fly down the patient over to the medical center, we can deploy the patient, move the patient to the nearest hospital, use one of these systems, and have the surgeon operating remotely. And this has the potential to dramatically reduce the cost of healthcare and the ease of delivery. So moving on to a more technical look at it, so we have two main packets that are being sent here. We have a surgeon-to-robot packet that we call the control packets, and this contains small differences in position, rotation, and grip information we call deltas, to say it simply. And then we have the packets coming back from the robot to the surgeon, which include haptic or touch feedback, video feedback, as well as status about the robot and the surgery. Now, this system has a lot of potential, but what happens when you consider security in this standpoint? Now, generalizing to cyber-physical systems in general, we've seen, attacks, staged attacks on power plants. The Stuxnet worm was widely publicized as an attack on Iranian nuclear systems. So what happens when we consider for surgical robots? Right now, it hasn't really been considered because the current robotic surgery systems are supposed to be implemented on dedicated private networks where the only two parties are the robot and the surgeon. So security hasn't really been part of the discussion. If we open this system to a more volatile, unreliable connection, such as the internet, where could we attack? Where could the possible attack vectors be? So the two major attack vectors we can come up with are either the endpoints or the network communication. Now, the endpoints open up some very interesting attacks, but most of them can be resolved through physical security or controlled access. So I'm going to ignore these ones for right now, and we're going to focus on the communication channel. So in our lab, we went ahead and set up a test environment. We have our surgeon control console running Windows 7. It communicates over to the Raven, which is running Ubuntu with the Raven code as a ROS module. And then we have a Kali Linux machine, that's our attacking machine, and this is all connected together with a network hub. We chose a network hub so we can emulate both observer attacks as well as man-in-the-middle attacks. Two small notes. One, the feedback that we get is camera feedback, and it's outside the network to reduce latency. And the second big thing here is the packets are modified UDP. Now, this was a decision the Raven team made because the the overhead of using a stream socket like TCP introduces a lot of delays in the operation process. And UDP allows us to, since we're sending a bunch of small changes, small deltas, the cost of loss is minimized if we send at a fast enough rate. So this is optimized for real-time movement, not so much for security. So we decided to try a couple of attacks on these systems. We had three major categories of attacks. The first one was intention modification. This is directly modifying the surgeon's actions. So from a technical perspective, we have our Kali Linux acting as a man in the middle, and we're looking at these packets coming through and modifying one or more of these elements. So we have a small video demonstration here. I'll play it for you guys so you can kind of look at it, and then I'll show you what we did to it. So if you look at the bottom right, we have Andy, one of our subjects, operating the robot. We have the robot arms in the main frame. In the top right, it's a little bit off sync, but we have our console where we're sending our attacks. Now, if you look carefully, you'll see at some points there is inconsistent movement patterns. Like, for example, right here, just now, the left hand was moving the right arm, and now it's switched back. And you'll see here he tries to move hands by switching grips, and we flip the grips at the same time that caused him to drop the block. And in a real surgical situation, something like this could be very dangerous. If you have one of the arms holding, say, a sharp object like a saw of some sort, dropping it could potentially cause some very serious damage. So this was our first attack. The second attack we came up with are intention manipulation attacks. Again, they're another man-in-the-middle attack, but these ones focus on the feedback packets, modifying the feedback so the surgeon makes a different decision based on what he assumes is good information. So looking at the feedback packet, there are a couple interesting attacks we could do. One that we found particularly interesting was modifying the haptic feedback. We could suppose that a surgeon is operating close to the liver. Now, the liver feels different from other tissues, so if we remove or eliminate haptic feedback, we could potentially confuse the surgeon as to what tissue he's actually operating on. Another one we can play with is video feedback, looping, reducing the quality, dropping video frames. And the last one we could fix is the robot status, where we can trick the controller to think the surgery is complete, or there's an error with one of the arms, and so on and so forth. The last one we have is hijacking. This is temporarily or permanently obtaining control of the robot. Now, we play around with the control packets again, but this time we're playing around with the sequence numbers. So looking at our diagram here, we have our setup. The controller is sending packets at 1,000 per second. Raven is programmed to to ignore any packets below the last seen sequence number, and to do a software reset if it goes more than 1,000 packets ahead. This will halt the surgery, and then the operators have to manually reset it. So suppose surgeon control console is sending packet 1, packet 2, packet 3. All we have to do is just add to the current packet number such that it's enough for us to take control, but not enough to reset the whole surgery. So when the Raven sees these packets, it sees 1, 2, and 3 and says, oh, these are behind, and go ahead, and it takes our commands. And if we want to resume the surgery back to the surgeon, we can just stop sending the packets, and then everything works perfectly fine. I have another little demonstration for you here. So in the bottom right, we have our operator, and working on the system as normal. And if you look here in a second, the left arm will not move, but the subject is not moving left arm right here. And then we stop the attack, and everything goes back to normal. Now, these attacks are very simple, but this is precisely the reason why they're so dangerous. A simple script kiddie could quickly write something up that could cause a lot of these problems. So what effect can this have on the parties involved? The first one, obviously, is the patient. This tool can be very powerful, and it can cause moderate to severe internal wounds on the patient. It can delay the surgery, which can increase the time under anesthesia, which can cause other medical problems. And in some cases, it could cause death. Even if someone can see that something's wrong, by the time it actually happens, the surgeon or the nurse may not be able to react quickly enough to cause to halt the surgery, which can still cause injury to the patient. In regards to the surgeon, we have an increased risk of operational error, even if they know that there's something wrong and they still continue to operate, like in time-sensitive surgeries or critical surgeries. But there are also some cases where the surgeon may not even be aware of the attack, such as removing haptic feedback or reducing haptic feedback. In terms of legal liabilities, the surgeon could potentially be held legally liable if, say, 90% of other surgeons would not make the decision that this surgeon made and continue the surgery. And one idea we had of attacking this way would be to slowly introduce either delays or some manipulation to the feedback packets such that the surgeon gets used to a severe delay and causes a mistake unknowingly. If the surgeon decides not to continue, then they wouldn't be held responsible for the attack. The robot obviously is vulnerable in this case. We had a lot of cases where we introduced a delta that was too quick and nearly damaged our nearby equipment, so that you can increase repair costs and increase the downtime of the system. Looking at the bigger scale, the industry, we have a couple big things. First, undermining public faith. Whenever a lot of these cyber-physical systems are attacked, we see a reduction of public faith in these systems. We predict that we'll see something even more with the attack of surgical systems because they deal directly with human life. If these systems become unreliable, insurance companies may refuse to cover it if it's a high enough risk, and so that will kill the industry very quickly. And also, the manufacturer could be held liable if they don't take appropriate precautions. So we've outlined some of the problems, and some of them are very serious. So what can we do to solve this? Well, the first solution that comes to mind is encryption to mitigate man-in-the-middle attacks. There's two main ways we thought of doing this. We could do either public-private key encryption or use some form of out-of-band authentication, like a phone or external messaging. But the problem here is it may reduce real-time responsiveness if it adds even a millisecond delay in the operation of the system. We found in a lot of our tests with surgeons that even a slight delay can cause virtual inoperability or an unreliable delay. The second thing we could do is link monitoring to prevent injection attacks. One thing we noticed on the logs of the Raven is when we did these injection attacks, we could see these two streams going along. And so we think we could add in monitoring algorithms to look and see when this takes place, but also monitor the safety and the state of the operation, the state of the network, to determine if it's safe to continue such any operation. And the last one we have is hardware protection. So limit the processing rate so you can't hold up, say, 50,000 packets and then just stream them all at once. That could really severely damage the servos and motors. And the second thing is expanding on the bounding box feature for joints. So Raven allows you to define a box where the joints are not allowed to go outside. If you go outside, it emergency stops and halts the operation. We think we could expand on this by limiting speeds in certain regions, say close to the heart or close to sensitive organs. One thing I wanted to discuss briefly is just the overall issue of cyber-physical systems, the design issues that come with this. We end up seeing this paradigm of security, safety, and usability that was hinted at a lot of the previous talks. Let me explain this in an example. Raven has an e-stop functionality. It's either a manual or automatically triggered stop system that will halt the operation and will allow someone to a time to fix the problems and reset. From a safety perspective, this is great. It allows a quick shutdown of the system, and we can either automate it or run it manually. Usability, well, it's a big red button, so it's pretty easy to use. It requires minimal to no configuration. But the problem we have here is security. Suppose that I want to if I want to just halt a surgery, I send a packet that's 10,000 beyond what the current sequence number is, and I halt the surgery. And then everyone tries to figure out what's wrong with it, then continue. And I can do it again and again. So I could make the surgery virtually inoperable and cause this delay and potential health issues. So this is something that really needs to be considered when designing a lot of these cyber-physical systems, not just in medical, with medical technologies, but cyber-physical systems like industrial systems in general. We very easily see that something that is good for safety and usability might be bad for security and vice versa, and leaving out the feature is not really a feasible option. So what are the next steps we should take from this? So teleoperated surgery is making a rise, and it's becoming the future of surgery. And it's a very amazing technology if it's implemented correctly, and it can introduce a lot of risks to patients and surgeons. So if we can identify the problems of these technologies and the problems in cyber-physical systems today, we can stop them and mitigate a lot of these problems while this technology is still young. Thank you. When the FDA approves these systems. Right now the system is under development. I got a chance to meet some of the people who are working on these systems. And it's really cool, but there's still a lot, even just from standard operation, that still needs to be ironed out. There's a lot of new problems are introduced by adding these challenges of operating on an open network.
Ann Cox, DHS. So if you're in Washington and operating in Alaska, so how do you handle the satellite bounce?
Sorry?
How do you handle the satellite bounce?
The satellite bounce. We haven't really, that's a good question. We haven't really considered something like this. We wanted to eliminate a lot of those external variables and just look at what we could do just simply with the system. This issue is a bit more on the design of the Raven itself, which I'm not very familiar with.
So are you working with the company to correct these issues?
So we've brought these issues up to the company, and they've definitely considered, they're putting it on a plan to fix these issues, but we wanted to bring up a lot of these issues early on because they reach out to a lot of cyber-physical systems.
Thank you for a good talk. I'm Ross Capel, University of Pennsylvania. So there's a lot of research on the Da Vinci in relation to prostate surgery, and it shows that it's either no better than manual surgery or perhaps a little worse, although hospitals are advertising it as, be-all. My question is that your suggestion here introduces another economic metric, which is it better than having a not superbly trained surgeon in Alaska doing it, which is a different question, right? And also the cost of not having a urologist in the middle of nowhere. So that's a great question that changes the conventional research about Da Vinci versus regular surgery to Da Vinci versus either suboptimal surgery or none.
Yeah, I mean, my understanding.
You want to use this one?
My understanding of many of these systems is that you take regions that might have had a surgeon and they don't have to have one anymore because they can do this. So you can reduce the number of skilled surgeons. Oh, okay. That's all I wanted to say. No comments on thought of this.
No, I mean, this is definitely something that needs to be considered, but in our preliminary research, we haven't had a chance to really look at this.
To kind of amplify the question before about what about the issue of latency and delay, In particular, since teleoperated surgery is considered as a solution for regions that are underserved by modern medicine, like third world and whatnot, where networks are notoriously unpredictable. So what would happen if the network itself drops for a couple of seconds or whatever? What happens then?
I believe Raven's default response, at least when we're using it, is to, if it doesn't see a packet for, I think it's 1 or 2 seconds, it marks it as a halt and gives notification to whoever's operating it.
Mm-hmm.
I'm not sure how the design team has responded to that.
But at the same time, if you said during your talk that real good surgeons are able to detect delays that are measured in the ones of milliseconds, and you're talking about a 1 second turn, that detection for the network having dropped, is that a problem?
Sorry?
Is that a problem? If the system can detect that, hey, the network went away after a 1 second delay, but the surgeon has issues as within ones of milliseconds of the network not returning feedback data, how do you deal with that?
That's a great question. I think right now, I believe we're considering that, right now it's being, Ravens deals with that case as latency, but we don't really have any way of monitoring the performance of the network to really be able to respond in a great way to that.
Yeah, because that the network itself seems like an externality to the endpoint systems, and it's kind of hard to detect problems at the network within the endpoints. So.
Yeah, to say a little bit on the scenarios I know for this, like imagine a hospital in New Orleans that doesn't have a prostate cancer surgeon but would like to be in the business of treating prostate cancer.
Mm-hmm.
So they make a deal with MD Anderson to do remote surgeries in New Orleans. You might have other surgeons in New Orleans actually who do it, but they're at other hospitals.
Mm-hmm.
And so that the latency, I think this one's an actual scenario, so that the latency would be from Dallas to New Orleans for those cases.
Yeah, okay.
I believe in terms of, in the couple of delay experiments we did, the surgeons were able to deal with, I think it was 250 milliseconds of delay, and then any more we started getting erroneous behavior. That's what I recall.
Yeah, there's another thing that's related to this. I don't know how this technology is used, but they have stabilization protocols like working on real-time systems for a beating heart so that you can take a knife and it will go up and down with the heart. So to the person doing the surgery, it looks as if the heart is still. And so that you might be able to smooth out the latency a little bit with some mechanisms that would give some feedback that would help with that. So.